Yeah, so dear students, welcome back after the break. So, before the break we are talking about the numerical examples of the current mirror as you can see here, and there we have used beta helper to improve the non-ideality factor coming due to the base current loss, namely this base current loss. So, in the next example what we will see that improvisation of the numeric current mirror circuit to take care of the non-ideality factor due to early voltage. To be more precise, we like to place one cascode transistor here and that improves the output resistance of the current mirror. So, in the next example, here we do have first we are starting with MOSFET version and then after that we will go to the BJT version. So, here transistor 3 it has been added on the main current mirror. So, the main current mirror it is constructed by M1 and M2 and whatever the reference current it is coming, it is mirroring here. And then we do have this transistor M3 to have meaningful operation of this circuit, we require its gate voltage V bias denoted here V bias, it should be sufficiently high, so that transistor 2 and maybe 3 also are in saturation region of operation. So, and of course, we do have the application circuit here. Now, coming to the different sizes of different transistors given here, we do have for transistor 1, we do have the K into W by L, it is 1 milliampere per volt square. On the other hand, for transistor 2 and transistor 3, we do have K into W by L equals to 4 milliampere per volt square. This is just for a change, we are using different values of the aspect ratio. Threshold voltage on the other hand, we are keeping it same for simplicity of the calculation, and also the lambda of all the transistors. It is not only for transistor 2, but for all transistors. Let you consider this is equal to 0.01 per volt. And then we do have the bias resistor which is 19 kilo ohms, and then V bias it is 5 volt, here it is 5 volt, and supply this should be VDD. So, this is 12 volt. Now, we need to find the value of this VGS1 and the current flowing here from whatever the voltage 12 volt it is given to us, and then R bias it is given there. So, to calculate that in some of our previous examples we have done that this current which is IDS1, it is also creating a drop here, and after subtracting this drop, say VR bias from 12 volt supply, it is giving us the VGS. So, we can say that VGS1 equals to VDD. So, VGS1 equals to VDD minus the IDS current multiplied by R bias. And on the other hand, we know that IDS, expression of IDS equals to K W by L of transistor 1 by 2, and then VGS1 minus VTH square, of course, by dropping the rest of the part. So, if I drop this part, and what we do have the expression of IDS here. So, we can put the expression of IDS here, and then we can make probably we can take the VDD on the other side. So, we can say that VDD minus VGS 1 equals to the R bias multiplied by IDS, and IDS expression it is given to us, which is K W by L by 2 into VGS minus VTH square. Now, we do have VGS also need to be find out. So, what we can do for simplicity, let you consider we add VTH 1 here, so that we can write this is minus with VGS 1, but then since we are adding it, we also have to subtract here the same VTH. So, we do have VDD minus VTH equals to this part, and again VGS minus VTH is also appearing here in the second order form. So, if I consider VGS 1 minus VTH equals to say x, then we can rewrite this VDD minus VTH. So, this part it is 12 volt minus VTH, it is given to us 1.5. So, that is 10.5 minus x minus R bias, it is 19, and this part it is 1 divided by 2 here. So, we can, and also we do have kilo ohms here, and this is in milliampere. So, again that is getting cancelled. So, we do have 19 here by 2 into x square. So, we can rearrange this equation. We can write in the form of 19 x square plus 2 x minus 21 equals to 0. In fact, that gives us solution of this x, which is equal to minus 2. We have to consider only plus term, because we are considering VGS minus VTH should be positive. So, this then 4 plus 4 into 21 into 19 divided by 2 into 19. In fact, that gives us a solution x is equal to 1. So, that means this is equal to 1. So, that gives us VGS 1 equals to VTH plus 1. So, this is equal to 1 plus VTH is 1.5. So, that is equal to 2.5. So, we got the voltage here, it is 2.5, and the corresponding current, if we put the value of this x is equal to 1 here, then we do get IDS 1 equals to 0.5 milliampere, right. In fact, so this is equal to 0.5 milliampere. Now, we need to find what will be the value of V2. V2 is the voltage coming here, and here we assume that both this transistor and this transistor, they do have K into W by L, which is 4 times than this one, which means that the current flow here, it is 4 times of this current, which is 0.5 here, and so that gives us IDS 2 equals to 4 into 0.5, that is 2 milliampere. So, if we do have this 2 milliampere current is flowing, and the same current is flowing here also, and the VGS here it is same. Since dimensions of transistor 2 and transistor 3 they are equal, and if I assume transistor 3 it is in saturation region, then the corresponding VGS here it will be same as whatever the voltage you do have, namely 2.5. So, if the VGS 3 it is 2.5, then voltage coming here which is V2. So, that is equal to V bias, that is 5 volt, minus VGS 3. So, that is equal to 2.5. So, we do have DC voltage here, it is 2.5. In fact, this is the hint it is given that we can consider both the transistors are in saturation, and if we assume that VDS of the two transistors, that ensures that VGS 3 equals to VGS 2, because we do have same transconductance of the two transistors. Now, so now we obtain we have solved this part. Next thing is that for V 3, if it is a 5 volt, then what we do expect? Here we do have 2.5. So, VDS 3. So, V 3 equals to 5 volt, that makes VDS 3 it is also 2.5, right. And with this voltage, we can try to find what will be the corresponding value of the output resistance R out, small signal R output resistance. So, yeah, so I am going to erase this board to create some space for the next calculation, but you please keep in mind that the current flow in this branch it is 0.2, current flow here it is 4 times of that, 2 milliampere. So, we need to find what will be the small signal output resistance, and R out is GM 3 multiplied by R O 3 or RDS 3 multiplied by RDS 2 plus R O 3 plus R O 2. Note that R O and RDS we are considering they are synonymous. Now, R O 2, in fact, all the transistors we assume that lambda is equal to 0.01. So, R O 2 it is 1 by lambda 0.01 multiplied by its current, which is 2 milliampere, and that gives us the resistance equals to 50 kilo ohm. So, same thing R O 3 equals to 50 kilo ohm, and on the other hand GM 3, and as I said that the current flow here it is 2 milliampere, and the VGS DC voltage here it is 2.5 or VGS minus VTH is 1 volt. So, that gives us the GM 3 which is by utilizing say K value here, K into W by L of 4. So, we can say 4 milliampere per volt, and hence the R out we are getting here it is 4 milli multiplied by 50 K here into 50 K, and then we do have 50 and 50 here. So, that gives us 100 K. In fact, this is becoming 10.1 mega ohm resistance. Okay. So, that is the small signal output resistance. Now, utilizing this information, can we calculate what will be the current flow in this branch IDS 3, or you may call IDS 2 also, for V 3 equal to 8 volt. So, how do you calculate? We can use this information, we can use the information of the current at 5 volt. So, we know that if V 3 it is equal to 5 volt, the corresponding current, it was the corresponding current here, it was 2 milliampere, and then if we increase this V 3 from 5 volt to 8 volt, due to output resistance, it is having some slope here, and we know that inverse of this slope, which is the output resistance, it is given here. So, using that slope and this voltage change, which is 3 volt, we can find what is the additional current here. So, you may call this is delta of this current. So, delta of this current, it will be 3 volt divided by whatever 10 mega ohms. Okay. So, we do have, so this is equal to 3 into 10 to the power minus 7, right. So, this much of ampere. So, the corresponding current here at this point, it is 2 milliampere plus this one. So, we can see that this current equals to 2, so 0.0003 milliampere. Okay. Now, how do you get this voltage? So, this circuit, it is fine, we are getting very small change of this current because of this cascode transistor. So, even though the voltage at this point V 3, it is going from 5 volt to 8 volt, still we can see that the variation here, the current variation, it is very small, and hence it is meaningful to add this cascode transistor. But then it is little inconvenient to get this voltage, and to overcome this problem, what we can do, we can put a transistor here, which is also diode connected, and that produces a voltage, and that is normally that is what it is getting applied. So, in the next slide we do have that example. So, we are adding here transistor 4 to generate this bias here. Okay. But of course, the voltage coming here, it is now different from whatever the voltage you do have. So, for the same condition here, namely sizes of transistor 1, no, I have probably I have changed, yes, I have changed here just for a change. We consider K into W by L of transistor 1 and K into W by L of transistor 4. They are equal to 2 milliampere per volt square. On the other hand, for transistor 2 and transistor 3, we are retaining this to be 4 milliampere. VTH we are keeping it same, and all the lambdas are 0.01 per volt. Supply voltage it is 12 volt. So, we can try to calculate what may be this bias resistor. So, that the current flow here it is 1 milliampere. So, how do you find that? If I know this current is 1 milliampere, probably from this dimension we can find what is the corresponding VGS required and the VGS required, and then from that we can find what will be the voltage here, and then we can see what is the drop here, and from that we can calculate R bias. So, 1 milliampere of IDS IDS 1 equals to its corresponding K, which is 2 milliampere per volt square divided by 2 into VGS minus VTH square. Again we are dropping 1 plus lambda VDS part. So, so this is giving us VGS 1 minus VTH equals to 1 volt, and hence VGS 1 equals to 1 plus 1.5, that is 2.5 volt, and this is also giving us VGS 2 equals to 2.5 volt. So, that gives us the voltage here, it is 2.5 and 2.5. So, that is 5 volt. In fact, this 5 volt it is nicely getting generated for making a suitable bias for transistor 3. And R bias, then R bias equals to we do have 12 volt here minus 5 volt divided by 1 milliampere current, right. So, that is giving us 7 kilo ohm. So, that is how we can set this resistor. So, that the current here in the left branch it is 1 milliampere. Now, we can try to find the value of this IDS 3 in same way, and here now the ratio, aspect ratio of transistor 3 channel and transistor 1 channel it is 2. So, the IDS 2 equals to the reference current 1 milliampere multiplied by W by L of transistor 2 divided by W by L of transistor 1. So, that is 2. So, that is giving us 2 milliampere. So, now we obtain this part and this part. We can calculate the small signal output resistance similar to whatever the way we have done. So, output resistance here it will be in fact, since the current here it is remaining same and this is also remaining same. So, we are expecting that output resistance R out. So, here also it will be 10.1 mega ohms. So, next question is that what is the minimum value of this voltage here, so that we can enjoy this high output resistance. In other words, what should be the minimum value of this voltage, so that transistor 3 it is remaining in saturation region of operation. So, we know that the voltage here it is 5 volt. So, the minimum voltage here we require it is 5 volt minus VTH. So, the minimum voltage here it will be 5 volt is the gate voltage here minus VTH 1.5. So, that is equal to 3.5 volt. So, as long as this voltage it is higher than 3.5 volt, then we do get output resistance, it is very high. So, that is how we can make the output current very less sensitive to the voltage for improved current mirror, or which is referred as cascode, commonly known as cascode current mirror. And similar thing it can be done for BJT also. So, in the next slide, in the next example, example 6, we will see that. So, here as we have done before, we have added transistor Q3 to get higher resistance here and making this current insensitive to the output voltage variation. And instead of giving a bias here, independent bias here, similar to the previous circuit example in MOSFET, we have added transistor 4 in diode connected form, so that we can internally generate a voltage here, suitable voltage here. Now, here the dimensions of the information of different transistors are given. Namely, we consider these two transistors are identical, having reverse saturation current of 9.5 into 10 to the power minus 14 ampere. On the other hand, transistor 2 and transistor 3, they are identical, having the reverse saturation current, which is 1.9 into 10 to the power minus 13 ampere, which is just 2 times of this current. So, we can see that the reverse saturation current ratio here it is 1:2. Supply voltage it is 12 volt. So, the first part we need to find what will be the bias resistor, so that the current here it is 1 milliampere. Now, here for BJT getting the voltage here it is much simpler. We can always approximate that VB on is very close to 0.6. So, if this is 0.6 and then we do have one more 0.6. So, the voltage here it is 1.2 volt. So, that gives us the R bias. So, the R bias equals to 12 volt minus 1.2 volt divided by 1 milliampere. So, this is equal to 10.8 kilo ohms. So, for the subsequent part we can use the same R bias to maintain this current 1 milliampere. Next thing is that we need to find what will be the small signal output resistance, and then we can calculate what will be the corresponding current here for V3 is equal to 1.2 volt and 5.2 volt. So, for if I consider say V3 is equal to 1.2 volt, this is also 1.2 volt. So, that makes Vc here and Vc here they are similar. So, what we can see that both transistor 3 and transistor 2 they are in active region of operation, and that makes the corresponding current particularly whenever this is 1.2 volt and the voltage here and voltage here, making the two Vc voltage equal. So, that gives us IC3 particularly for this case equals to just Is ratio Is2 divided by Is1 into the reference current is 1 milliampere, and hence this is since the IS ratio it is 2. So, we can say it is equal to 2 milliampere. Now, once we have 2 milliampere of current, probably we can get the value of the R out and the corresponding particularly R O and then G M, and then we can find what is the corresponding output resistance of the current mirror. So, to calculate, let you consider R O 2. So, this is equals to we do have the early voltage 50 divided by 2 milliampere. So, that gives us 25 k. In fact, this is true for R O 3 also. So, that is equal to 25 k. On the other hand, GM of transistor 3. So, this is equal to IC by VT, IC by VT, thermal equivalent voltage. We can consider this is 26 millivolt VT. So, we can say this is equal to 1 by 13 mho. In fact, that gives us the output resistance R out equals to GM 3 into R O 2 multiplied by R O 3 plus R O 2 plus R O 3. In fact, what we can get here it is okay, let me use this space here. So, GM 3 it is 1 by 13, and then we do have 25 k into 25 k. So, this is this much of mega ohms, plus we do have summation of this to 25 k. So, that is 50 k, probably that you can ignore. In fact, you may calculate this one, but I think I do have some calculated value for you. So, this is becoming 48.127 mega ohms. Note that here I have ignored the R pi here. Otherwise, I should have to consider, instead of only this one, I should have to consider R O 2 in parallel with R pi 3, but this node it is not ground. In fact, from here to here I do have 1 by G M, and also we do have 1 by G M. So, I should have considered R pi 3 in series with 1 by G M 4 plus 1 by G M 1 instead of this one. But since we have considered beta is very high, we may say that this is infinite, and as a result I have dropped this part, and that gives us much higher resistance. Practically, you have to consider this R pi, and its value it may be much lower than this resistance. It may be in the range of say 1 k to 2 k. In fact, if I multiply this R pi 3 with G M 3, so that gives us the beta of the transistor, and the corresponding resistance it may vary, but even then this resistance it may be in the order of few mega ohms. So, anyway, for this numerical example, since the output resistance it is here, using this output resistance information, we can calculate the variation of this current. If we vary this V 3 from 1.2 volt to 5.2 volt, that means a voltage variation of 4 volt. So, for this voltage of V 3, we can calculate the corresponding I C 3 equals to 2 milliampere plus delta V, which is 4 volt. So, 5.2 minus 1.2 and divided by 48 mega ohms. And in fact, again I have done the calculation for you, and this is coming 2.00008 milliampere. That is again very close to whatever we do have. So, that indicates that by adding this cascode transistor, since the output resistance is very high, the variation here it is very small. This is again it is called the cascode current mirror, and by adding this transistor we are getting the advantage. Now, coming to other kind of example, instead of considering only the current mirror, if we consider some circuit where we have used the current mirror, namely in common source amplifier as well as in common emitter amplifier, where we have used the current mirror to create the active load. So, in the next example, we do have common source amplifier, I guess. Yes, we do have common source amplifier where we have the load part, that is active load here. Input we are feeding to transistor 1. So, transistor 1 it is working as the main amplifier, and then transistor 4 it is working as the active load. But then this active load it is getting biased from or through this current mirror, and our calculation of this numerical example is to find that how do you set the different meaningful value of these resistors and then current mirror. So, to start with, we do have the value of K into W by L of different transistors, namely transistor 1 and transistor 2. So, we do have transistor 1 and transistor 2. We are assuming they are identical, and on the other hand transistor 3 and transistor 4, they are PMOS transistors. They do have different value of this transconductance factor, but they are same. They are this transistor 3 and transistor 4, both of them are having this factor equal to 0.5 milliampere per volt square. Let you consider VTH for all the transistors. So, whether it is NMOS or PMOS, it is 1.5, and lambda for all the transistors, equals to 0.01. Supply voltage it is 12 volt. So, the first part we need to find what is the ratio this potential divider, so that it creates a voltage here such that the current flow here it is 1 milliampere. So, how do you find? We need to calculate what is the VGS required here to get 1 milliampere of current flow. So, again if you use this information and the 1 milliampere of current requirement, you can find that VGS equals VGS minus VTH equals to 1 volt, and that gives us VGS 1 equals to 2.5, and that gives us the ratio of R11 by R12 equals to VDD is 12 volt minus 2.5 divided by 2.5. In fact, this is equal to 9.5 by 2.5. or we can say this is 19 by 5. So, if you use this ratio for this part also, and that also sets this current equals to 1 milliampere. Okay. So, we are using the same value of this ratio, and for the subsequent part let me consider this ratio. Now, we need to find, next step it is we need to find the small signal output resistance and the voltage gain. So, we are expecting this will be setting the current here, right, which is 1 milliampere, keeping both transistor 1 and transistor 4 in saturation region of operation. So, the RO of transistor 1 which is equal to 1 by lambda, which is 0.01 multiplied by 1 milliampere of current. So, that is equal to 100 kilo ohm. Likewise, RO4 it is also 100 kilo ohm, and that gives us the output resistance of the amplifier equals to RO1 in parallel with RO4 equals to 50 kilo ohm. Now, to get the voltage gain, we need to calculate GM of transistor 1, and again by utilizing this information and VGS, we do get this is equal to 2 milliampere per volt, and that gives us the voltage gain AV equals to minus 2 milli per volt multiplied by this R out, which is 50 K, and that gives us a gain of 100. So, we got the voltage gain, we got the output resistance. Next thing is that what is the DC voltage? We know that these two currents they are equal, but both of them are having very high resistance, but we need to know what may be the precise value of this voltage. Will it be 6 volt, which is half of this voltage, or something else? We can keep that in mind, that the current flow here it is 1 milliampere, there we have ignored 1 plus lambda VDS part. And to define this voltage, we need to consider this 1 plus lambda VDS part to get the precise voltage. In fact, if you see it carefully, the current flow through this transistor and this transistor, they will be equal if they are corresponding VDS, they are equal, right. But then VDS of these two transistors, if you see VDS of this one output node voltage, since it is very sensitive and its output resistance is very high, it may be difficult to get, but then voltage getting at this point is not so difficult, because this transistor 3 it is diode connected. In fact, if you calculate what may be the VSG of this transistor by considering its size here and the corresponding current here, you can find that VSG of transistor 3 minus VTH of transistor 3. Since it is PMOS, we should consider magnitude. In fact, this is equal to since the current is 1 milliampere, but then K into W by L it is 0.5, VGS minus VTH square it is equal to 4, and VGS minus VTH is becoming 2. So, that gives us, I should say VSG, because it is PMOS. So, VSG 3 equals to 2 plus the threshold voltage 1.5. So, that gives us 3.5 volt. So, that sets this voltage here 12 minus 3.5, and this voltage it is 8.5 volt. In fact, if this voltage it is 8.5 and this is also 8.5, then only these two current they will be equal. In other words, this current flow of this transistor and current flow of this transistor, they are matched whenever these two voltages they are 8.5, and transistor 3 and transistor 4 they are also nicely supporting this conclusion that output voltage if it is 8.5, then the currents are equal. So, from that argument we can say that DC voltage, output DC voltage, instead of 6 volt, it is rather 8.5 volt. It is not 6 volt, right. So, similar kind of exercise we can do for the common emitter amplifier. So, in the next slide we will be having this common emitter amplifier, but then again we need to take a break. So, after the break we will come back. Thank you.